Hello everyone, welcome to week 10's discussion session. So let's begin our today's discussion session with the first question. Okay, so the first question is, for a 65 nanometer technology node, find the subthreshold leakage current for a 3-stack NMOS combination with NAND logic 000 in terms of the subthreshold leakage current for a single NMOS transistor with gate voltage 0, given that subthreshold slope is given, Debye coefficient is given, and body effect coefficient is given. Okay, so this is my S, this is my eta, this is my gamma or K gamma. Okay, different authors attribute it differently, so let us call it K gamma, body effect coefficient. Okay, so first of all, let me draw the NMOS stack, 3 transistor NMOS stack for a NAND logic of 000. Okay, so basically this is my pull down stack consisting of the NMOS, because NMOS has been asked here, and the inputs are 0 0 0. So here it would be VDD, right, because PMOS stack would be on and it would be the output node would be charged to VDD. Okay, so basically all this three are in off condition. Okay, so I have to find the subthreshold leakage current through this. Okay, now it is clear that as some current is flowing, there will be some voltage drop across the transistors. So let me call these two node voltages as Vx and Vy. Okay, and from the equation that has been provided to us of the subthreshold current, I will be finding the current for all these 3 transistors, and as these 3 are in series, so all the currents that I will be finding, these 3 currents that I will be finding, that will have 2 variables, this Vx and Vy will be equal to each other. And as I'm having 2 variables and I'm having 3 equations, I can easily solve it. Okay, so let us start. We know the equation of subthreshold current is I of, okay, like it is the simplified equation, 10 to the power Vgs plus eta is the Debye coefficient, into Vds minus Vdd, okay, minus K gamma, that is the body effect coefficient, and into Vsb, whole divided by subthreshold slope S. Okay, now let me call these 3 transistors as, let this one be transistor 1, this one be 2, this one be 3. Okay, now for the transistor 1, my I sub threshold, let me call it I sub 1. Okay, for this one it would be how much? It would be I of into 10 to the power Vgs. G is 0, S is Vx, so it would be 0 minus Vx, that is my Vgs, plus eta is how much? Eta is given as 100 millivolt per volt, so it is eta is basically 0.1 volt per volt. 100 millivolt is 0.1 volt, right? Eta into Vds. Drain here is Vdd, S here is Vx, so Vds is Vdd minus Vx, minus Vdd is again Vdd, so Vdd will cancel each out, minus K gamma is 0.066, and Vsb, basically these are NMOS transistors, so generally to eliminate this body effect, we connect the body of the NMOS to ground and body of the PMOS with VDD. Okay, so that body effect does not the body effect doesn't come into picture And also there is some power dissipation factors are also there, that if body source junction is gets positive bias, then my power dissipation increases, that is they become forward bias, current increases, so power dissipation increases. So, and also to remove this body effect completely, we ground the body of NMOS, and we apply VDD to the body of PMOS. Okay, but one more thing, we know that the threshold voltage of transistors can also be switched using this body terminal. So sometimes this can be used to tweak the threshold voltage of the devices, and that can be further used to design skewed inverters and something like that. Okay, so here K gamma is 0.066 into VSB, S is here Vx, B is here 0. Okay, divided by subthreshold slope, which is 0.1. So it becomes I of 10 to the power minus Vx plus 0.1, sorry, minus 0.1 Vx minus 0.066 Vx whole divided by 0.1. So let me call it equation number 1. Now for the second transistor, let me call it transistor 1, first transistor. Now for second transistor, now for transistor 2, that is this transistor, let me call the subthreshold current as I sub 2 will be equals to I of 10 to the power VGS, VG is here 0, Vs is here Vy, correct? Plus eta is 0.1, eta into VDS. VDS is VD is Vx and Vs is Vy, right? So VDS is Vx minus Vy. So VDS minus VDD. VDD is how much? VDD is 1 volt basically. Okay, so for 65 nanometer technology, VDD is 1 volt. Minus 1 minus K gamma is 0.066 0.066 into VSB. So Vs is Vy and Vb is body 0. Okay, so it will become I of into 10 to the power minus V divided by S. S is 0.1 subthreshold slope. So it will be I subthreshold leakage current of second transistor would be I of into 10 to the power minus Vy plus 0.1 Vx minus Vy minus 1 minus 0.066 into Vy whole divided by 0.1. Let me call it equation number 2. Okay, now for the third transistor, it would be for transistor 3, it would be, let me call the subthreshold current as I sub 3. It would be equals to I of 10 to the power VGS. So you can see here VGS would be 0 minus 0. Okay, so 0 minus 0 plus eta is 0.1. VDS would be Vy minus 0 minus VDD. Okay, plus sorry, minus K gamma is 0.066 into VSB. S is here 0, B is here 0, so it will be simply 0 minus 0 whole divided by subthreshold slope 0.1. So I subthreshold 3 is coming as I of into 10 to the power 0.1 Vy minus VDD is 1 divided by 0.1. Let me call it equation number 3. Okay, Fine. Clear? Okay, fine. Okay, fine. Okay, so now what I will be doing, I will be equating the equation 1, 2 and 3. So first let me equate equation 2 and 3. So from 2 and 3 we get, so from 2 and 3 we will be getting, see, I sub 2 equals to I sub of 3, correct? And you can see here I of 10 to the power is common, so I can simply cancel these two, or let me write it for you. I of 10 to the power minus Vy plus 0.1 Vx minus Vy minus 1 minus 0.066 Vy by 0.1 will be equals to I of into 10 to the power 0.1 Vy minus 1 by 0.1. So this will cancel, this will be cancelling each other. So what I'll get is minus Vy plus 0.1 Vx minus Vy minus 0.066 Vy will be equals to 0.1 Vy minus 0.1. Okay, so let me rewrite it. It will come as Vy will come here, so minus 0.2 Vy minus 1.2 Vy, so it will be coming as minus 1.266 Vy plus 0.1 Vx equals to 0. Let me call it equation number 4. Okay, fine. Now, okay, now from equation 1 and 3 we get, which is 1 and 3, this is 3 and this one is 1. Again I of n and 10 to the power will cancel each out, so let me simply write the variables that I'll be left with. So it will come as minus Vx minus 0.1 Vx minus k gamma is 0.066 Vx will be equals to 0.1 Vy minus Vdd. So eta into Vy, that is 0.1 into 1 will be 0.1. Okay, so if I simplify it, I'll be left with Vx minus 0.166. So 1.166 Vx plus 0.1 Vy equals to 0.1. Equation number 5. Let me call it equation number 5. Okay, fine. So now I have equation 4 and 5. So if I have two, I have two variables and 5 equations I am having, basically 4 and 5 I'll be solving. I'll be substituting, and I'll be substituting 5 in 4 or 4 in 5, and I'll be simply getting the values of Vx and Vy. Therefore, uh, so let me using 4 and 5. I'll be using 4 and substituting it in 5. So we get 1.166 Vx. Now what is it? Vx is 1.266 by 0.1 Vy. Okay, so 1.266 by 0.1 Vy plus 0.1 Vy equals to 0.1. If I solve it, I'll get Vy equals to 0.1 divided by 14.86156. Okay, which is coming as 6.728 millivolt. That is equals to 0.006728 volt. Correct? Okay. Again, now Vx would be simply from equation number 4. Vx would be how much? 1.266 by 0.1 into Vy is 0.006728, which will come as 12.66. Vy will be 0.0807 volt. So I know Vx, I know Vy. Now I know this is from 4. From 4. Okay, so now using one of the above equations, I can use which one? I can use any one. Third one is the simplest one. So I sub threshold will be equals to I0. Okay, so it's I0 or I of 10 to the power 0.1 Vy minus Vdd by S. So I of 10 to the power 0.1 by 0.1. Vy is, I have got the Vy as 0.006728 minus 1. So it will come as, if I solve it, it will come as 0.101 I of. This is my I sub threshold. Okay. So I sub threshold current is 0.101 I of. See, 0.1010 I1. This is the answer. Clear? The calculation can seem a bit lengthy, but the concept is easy. That you have to just, when such kind of circuits, such kind of problems are there, just find that which transistors are on, which are off, find the node voltages, and if you find the node voltages, like if you can identify the node voltages, then you can simply equate, write the current equation and simply equate them to find the node voltages and the corresponding subthreshold currents. Okay, fine. If it's clear, let's move to the next question. Question number 2. Okay, so question number 2 is find the same as question 1 for NAND logic of 100 and I1 5.63 nanoampere. Okay, so everything, all the parameters remain same, only now I have been given the NMOS stack. The input is 100. So let me draw the NMOS stack first. Okay, so it's 100. So this one is on, this one is off, this one is off. Okay, so if this is the case, so my PMOS, it is off basically, so my output would be VDD, right? because PMOS stack would be on in complementary MOS circuits. So my output, this is my output Y or OP, whatever you call. Okay, so this one would be high VDD, and my pull down stack will be off because two of the transistors, NMOS transistors, are off here. Okay, so what will be the voltages? See, simple. As this transistor will be acting as an pass transistor, and we know NMOS passes weak 1. Okay, so if VDD is given at the drain and gate is also having VDD at the source, you won't get VDD, you will get a slightly depleted voltage of VDD minus VT. We have seen it a number of times during our previous assignments, previous discussion sessions. Okay, because once VGS value, once this VG and this S, once VGS reaches VDD minus VT, my VGS should become VT. And if Vs tries to overcome this VDD minus VT value, my VGS value reduces, VGS minus VT becomes negative, so my transistor will become off and it won't charge the transistor, charge the output capacitor. So my maximum voltage that can it achieve is VDD minus VT. Okay, if like, and we have also seen if subthreshold current was present, it will charge to VDD, but it will take a lot of time and it will be impractical to talk about it at this stage. But yes, so this voltage will be VDD minus VT, and as these two transistors are off, so let me call this node as Vx. Okay, fine, because some subthreshold current will flow, some small amount of voltage drop will be there, so this, let me call this small amount of voltage drop in the node as at this node as Vx. Okay, so again my I subthreshold 1, so I'll get two equations now, for one for this one and one for this one. Let me call this transistor 1 and this is transistor 2. So my, take some space, I subthreshold for transistor 1 would be how much? I of into 10 to the power VGS. VG is 0, Vs is minus Vx, Vs is Vx, so it is minus Vx, plus eta is 0.1, VDS is VDD minus VT is VD, and Vs is Vx minus VDD. Okay, minus K gamma, let me write it as 0.066 into VSB. Vs is Vx, Vb is 0, whole divided by S. S is 0.1. Okay, so it would become I of into 10 to the power minus Vx plus 0.1, this VDD will cancel, minus Vx VT plus Vx minus 0.066 into Vx, whole divided by 0.1. Let me call it as equation 1. And for this transistor 2, I will get another equation. I subthreshold 2 would be equals to I of 10 to the power VGS. Vg is 0, Vs is also 0, eta is 0.1, VDS would be Vx minus 0, VDS is therefore Vx, so VDS minus VDD is VDD minus 0.066, that is K gamma, into VSB. Vs is 0, Vb is 0, all divided by 0.1, so it would become I of 10 to the power, VDD is 1 here, therefore it would become 0.1 Vx minus 0.1 by 0.1. We call it equation number 2. Sorry. So now Now simply okay, so now using equation 1 and 2, from 1 and 2, if I equate them to both the equations, because I sub 1 will be equals to I sub 2 because they are in series, equals to I sub threshold, I'll get I of and 10 will cancel each other, so I'll get minus Vx minus 0.1 Vt is 0.3, let me simply write it 0.3 plus Vx minus 0.066 Vx equals to 0.1 Vx minus 0.1. Okay, so Vx would come as, so two equations and one variable, I can simply solve it. So Vx would come as minus 0.07 by 1 minus 1.266. So it will come as 0.05529 volts. Okay, clear? Fine. So now let me put it in equation 2. Putting Vx in equation 2, I will get I sub as I of is given as how much? I of is given as 5.63 nanoampere. 5.63 nano into 10 to the power 0.1 into Vx is 0.05529 minus 0.1 divided by 0.1 comes as 5.63 nano into 0.113, which is equals to 0.6394 nanoampere. This is the answer. Okay, so 0.6394, that is 0.64 nanoampere. This is the answer. Clear? How we are getting it? Sorry. So basically, if you can identify the node voltages and if you equate the currents, then you can solve any such problem. Okay, you can find the subthreshold current for any such stack. For two variables, I need how many equations? 3 equations, right? And for one variable, I need 2 equations to solve it. Fine. For unique solutions. Okay. Question. Now let's move to the next question. Question number 3. What is given? Given that I gate for NMOS is 6.3 nanoampere, find the gate leakage current for the NAND gate logic 1 on 0. Use the parameters mentioned in question number 1. Okay, an interesting question. Let me draw it. Fine. 1 1 0. So on and off. Okay, so they have asked us to find the gate leakage current, not the subthreshold leakage current, the gate leakage current. And we know gate leakage current only comes for on transistors. So these two are our transistors of interest and not this one. Okay, now if you remember, the gate leakage current is such that it only comes to picture if the VGS is significantly high, like around VDD. So if my VGS is around VDD, then only my gate leakage current would come into picture. If it is 0 or near Vt, it will not come into the gate leakage current will not consider it, because it will be too small to consider. Okay, it will not come into picture. So let us find the node voltages. You can see here the node voltage here would be, as it is a pass transistor, this transistor is working as a pass transistor, this voltage would be VDD minus VT, correct? And this voltage would also be VDD minus VT, because here it is VDD, here also VDD, so it cannot pass VDD, but once it has passed VDD minus VT, this can be easily passed even to the next node. Okay, so let me call it the first transistor, let me call it the second transistor. Now the VGS for the first transistor would be how much? VDD minus VG is VDD and VS is VDD minus VT, so it's around VT. And even for second transistor, my VGS would be VDD minus VT, so it's around VT. So as these VGS values are too small, my current, my gate leakage current, okay, let me call it IGS1 and IGS2, would be negligible, it would be almost zero. Okay, so therefore my I gate, okay, I gate will be, actually I gate is sum of all the leakage currents, because if current was flowing, then all of them would have contributed to all these two would have contributed to the leakage, then it would be sum of these two, IGS1 and plus IGS2, but as both are 0, it would be 0 plus 0 equals to 0. Okay, so current answer is 0 ampere. Okay, now it has not been asked here to find the subthreshold current, but as question has been given, let us also find the subthreshold current here. It would be easy, because only one transistor is off here, this transistor is only off, I have to consider this transistor only, let me call it as transistor 3. Subthreshold has not been asked, but I am finding it, okay, because more the merrier in terms of practice, more we practice, it's better for us. So I1 10 to the power VGS, VG is 0, VS is 0, plus eta is 0.1, VDS, sure. Actually you have missed, I think, the first part I have written there. Okay, let me write it again. It will be VGS minus eta is the Dibble coefficient, into VDS minus VDD, okay, minus K gamma, or gamma the body effect coefficient, into VBS. It is VBS or VSB? It is VSB, sorry, it is VSB, whole divided by the subthreshold slope S. Okay, so it would become I1 into 10 to the power, VG is 0, VG is 0, VS is also 0, so 0 minus 0 0 minus eta is 0.1, eta is given as 0.1, okay, 100 millivolt per volt, so it's 0.1 volt per volt, into VDS, VD is VDD minus VT, VS is 0, VD minus VDD, minus K gamma is 0.066, into VSB, VB is 0, VS is also 0, so 0 minus 0, whole divided by S is 0.1. So I1 10 to the power, this VDD will cancel, 0.1 VT by 0.1, correct? So VT is around 0.3, and I1 is given as for NMOS it is, I think, 6.3 nano into 10 to the power minus 0.3, so it will come as 3.1574 nanoampere. Clear? I subthreshold has not been asked, but I have found it, so that you can understand how, like, for any combination you can find it. This is the answer if subthreshold current was asked. Clear? Take, okay, fine. Then let's move to the next question. Question number 4. So it has been asked that for 65 nanometer technology node, find the subthreshold leakage current for a 2-NOR logic with input 1 1, given that subthreshold slope, Duval coefficient, body effect coefficient, subthreshold leakage current for single NMOS and subthreshold leakage current for single PMOS transistors are given. Okay, so this is my S, this is my eta, this is my gamma or K gamma, whatever you call it. So it is I subthreshold for NMOS, this is I subthreshold for PMOS. Okay, so basically this is the off one. Okay, let's find it out. It is given that it is a 2-input NOR. So let us draw the 2-input NOR first. Till now we have seen for NAND, now we'll be looking for NOR. This is my output, this is my VDD. So the input is 1 1, so this would be on, this would be on, this one would also be on, whereas this two would be off, right? Because 1 1 PMOS would be off. Okay, okay, so my this stack would not come into picture, this stack would not come into picture, this one will not come into picture, and I have to consider this because subthreshold current have, occurs for off transistors, right? So let me take into consideration my pull-up stack. So pull-up stack will be something like this. Output would be how much? 0, because my NMOS is working and PMOS is in off state. So 1 1. And what would be the voltages? As it is, this transistor is off, so here VDD minus VT, VDD will not pass, and only there will be some small voltage here at this terminal due to the subthreshold current. So let me call it as Vx. Okay, so my subthreshold current, let me call it the transistor, let me call it the transistor 1 and transistor 2. So for transistor 1, my subthreshold current I sub 1 be how much? If you remember the formula just that I have written just now, it would be, and for PMOS, let me write the formula again, it will be easy for you. VGS would become simply VSG eta, VDS would become VSD minus VDD, and K gamma, VSB would become VBS. See, there are two nomenclatures, you can follow either. You can either every time you move from NMOS to PMOS, you can invert the VGS to VSG, VDS to VSD, and so on, VSB to VBS, and so on. Else you can keep everything exact, that is VGS you will keep as VGS only, VDS will keep as VDS only, VSB and VSB only. Only what you need to do, you need to take all this as negative. Remember that VDS, VGS, VSB, what else, not mu, that Kn, everything, everything will be considered negative. Okay, so all the parameters, that the levels 1 spice model parameters that I have discussed way back, all these 5 or 6 parameters would be negative. You can consider either of the nomenclature. They are basically same only, but it's helpful to solve numericals if you stick to either, any one of them. Okay, here I have just reversed the VGS to VSG for simplicity, but that nomenclature is also fine, and generally the delta one is preferably used in many cases. Okay, so here, okay, as PMOS is asked, so we'll be taking the I of s 0.93, sorry 9.3 nano. Okay, let me keep it as I of only as for now. So VSG. So for transistor 1, my Vs is VDD, VG is also VDD, this one, eta is 0.1, Vs is VDD, Vd is Vx minus VDD minus K gamma, Vb is VDD, and Vs is Vx divided by S. Cancel, cancel. I'll be left with I of 10.1 minus Vx plus K gamma is 0.066, VDD is 1, and Vx would be, so it would become 0.066 Vx. Paper point. Question number 1. Okay, fine. Now for the second one, I subthreshold current for transistor 2. For this transistor, this one we have considered. Now this one would be I of 10 to the power VSG. Vs is here Vx, Vg is 1, am I writing something wrong? No, it's fine. Vx minus 1 plus V eta is 0.1, Vsd, Vs is Vx, Vd is 0 minus VDD minus K gamma, Vb would be VDD, Vs is Vx whole divided by S. S is 0.1, so it will become I of 10 to the power, if I solve it, it would become Vx minus 1. Well, don't let Vx minus 1, let me keep it like this only. Vx minus 1 K comma 1 minus Vx. We call it as equation 2. And let me check the equation 1 once again whether I made any mistake or not. VDD cancel, VDD cancels 0.1 Vx. Sorry, here if you see here the VBS term, VB is here VDD, okay, VB is here VDD and VS is also VDD, right? So it will not be Vx, it will be VDD minus VDD. So K gamma term will not come into picture. So it would be, equation 1 would be I of 10 to the power minus 0.1 Vx by 0.1. Okay, so let me equate equation 1 and 2. So from 1 and 2 we get I of and 10 would cancel each other, so I'll be left with minus 0.1 Vx equals to Vx minus 1 plus 0.1 Vx minus 1 minus 0.0661 minus Vx. Take Vx as common. 1 plus 0.1 plus 0.1 plus 0.066 equals to 0.1 plus 0.066 plus 1 implies Vx will be equals to 1.166 by 1.266, come as 0.9210 volt. Therefore, substituting Vx in equation number 1, we get I sub, that is I sub threshold current, would be equals to I of is 9.3 nano into 10 to the power minus 0.1 by 0.1, 0.1 cancel, into Vx. Vx is 0.92101. It will come as 1.115 nanoampere. Okay, this is the answer. Clear? So answer is 1.115 nanoampere. Clear? So be it any stack, just find the node voltages, equate the currents of subthreshold, and you'll be able to solve for the unknown variable, the node voltages. Then you can simply find the subthreshold current. If gate leakage current is there, then you can find that one also. And like I would like to add one point, like we are talking about gate. If I apply voltage to gate, there is some leakage. Now why this leakage is happening? One of the reasons you can think of, that what happens, we apply a positive voltage to a band, it goes down, right? So when you are applying positive voltage in the gate terminal, if the voltage is high, it might happen that the energy band of the gate gets lower, and a tunneling effect can start, because the band is getting lower. If it gets if it gets small, tunneling can start, and that's why we get this this current. Sometimes it is also called GIDL, gate induced drain lowering, or something like this. These effects also come into picture, and we get this gate leakage. Okay, this is the origin of gate leakage actually. Okay, let's move to the next question, question number 5. So what it has been given, find the static power consumption of a chip designed to the following specification. I subthreshold leakage for low VT is given, I subthreshold leakage for high VT is given, I gate is given, my lambda is given, and 10 to the power 9 transistor is used to design the chip, out of which 15 to 10 to the power transistors are logic devices with W equals to 12 lambda, activity factor of 0.1. Activity factor is not required for static power, it is required only for switching power or dynamic power. And it has been mentioned that 95% of the devices are low leakage devices in logic devices, and 5% of the logic devices are high leakage devices. Now low leakage means high VT. If VT is high, then only leakage will be low. And high leakage devices mean low VT. So I know which one to use when. Okay. Memory devices consist of 915 10 to the power 6 transistors. So you can see most of the devices are memory devices. Activity factor of 0.02, which is not required for static power distribution, W of 4 lambda. And here 100% of the devices are low leakage devices. Low leakage means high VT devices. Okay, so now let's find it out. Okay. So these are my number of memory devices, these are my number of these are number of memory devices, these are number of logic devices. Okay, fine. So let us find for the logic devices first. Subthreshold current for logic devices, let me write it as I sub L. It would be how much? NL into subthreshold current, simple. And subthreshold current would be of two types. for low VT plus high VT. Correct? Now these currents, if you see, these currents are given as current per length. What length? Width. Current per width. So here, as these values are given as not I but I by W, that is current per unit W. So to get the net, I have to multiply this term with W. Okay, and this is basically my current per unit width. This is what has been given to us, what has been reported and given to us. Okay, so it would be basically I subthreshold leakage would be implies I subthreshold leakage logic devices would be NL is how much? 50 into 10 to the power 6. W is 12 lambda. Lambda is 25 nanometer. Let me convert into micrometer, then it will be 0.025 micrometer. IL per unit W for low VT is how much? 100 nano per micrometer, plus IL for high VT is 10 nano per micrometer. So micro can cancel. So I'll be left with how much? 12, 5, 60, 600. So it will become 6 into 25. So and one more thing, as I have to consider the total number of transistors that are low VT and high VT in each cases, right? So there will be another term here. It would be as 5% of the devices are low VT devices, so I have to multiply it 0.05, that is 5%, correct, plus for 10 nanoampere, that is high VT, 95% of the devices, so 0.95 ampere. Correct. So I'll be getting the it as 9.5 plus 5, so it will become 0.2175 ampere. Okay, therefore I subthreshold for logic would be 0.2175 ampere. Now for I subthreshold memory, I'll be following the same logic. There will be number of memory devices into W into I subthreshold per unit width that has been reported, and 100% of the devices are what high VT devices, so 950 into 10 to the power 6 that has been given, this one, into W is here W was 12 lambda and 12 lambda, here W is 4 lambda, so 4 into lambda is 0.025 micrometer. Okay, and current is 10 nanoampere per micrometer, so it will come as 0.95 ampere. So my total subthreshold current would be I subthreshold total would be sum of subthreshold current for logic plus subthreshold current for memory, so 0.2175 plus 0.95 ampere, which will come as 1.1675 ampere. Correct? All good? Now I have to find the gate leakage current as well. Therefore my I gate leakage. Now one thing, if you remember the lecture that sir has told, the gate leakage current for PMOS is very small, so we don't consider it, we consider it to be 0. Okay, but here I will not be considering whether my transistors are NMOS or PMOS. For all the transistors I will be considering as NMOS only. But generally memory devices consist, logic of course consists of PMOS and NMOS, And memory devices also consists of, uh, if it is made up of some kind of SRAM cell, then both PMOS and NMOS are involved. If uh, DRAMs are used, or if other flash memories are used, which they are basically NMOS devices only. Okay, but here I will be not considering the fact that whether my memory devices are PMOS or NMOS. I will be considering gate leakage due to all the transistors only. Okay, so I gate leakage should be where it has been given, it should be given, yes, I gate is given as 5 nanoampere per micrometer. I gate per unit W into number of memory elements into width of memory elements plus number of logic elements into width of logic elements. I gate by W is given as 5 nano ampere per micrometer. Nm is 950 into 10 to the power 6, and it is 4 lambda, so 4 into 0.0025 micrometer, plus NL is 15 to 10 to the power 6 into 12 lambda, right? So 12 into 0.025 micrometer. So it will come as 10 to the power 9 into, not 10 to the power 9, it will be how much? 5 nano into 95 into 10 to the power 6 plus 15 into 10 to the power 6, 110, so 550. So 550 minus 3, so it would be 0.55 ampere. Therefore I gate leakage is 0.55 ampere. Okay, now total threshold, I have to find the power dissipation, right? Total power consumption. Therefore total power dissipation would be I subthreshold plus I gate leakage by 2 into VDD. Now you will say why 2? Why divided by 2? Because I am considering that for 50% of the time each of my logic or memory devices is on. So basically when my subthreshold will be on, when the transistor will be on, it will only result in gate leakage, and subthreshold leakage will be 0. When it will be in off condition, my subthreshold will be there, but gate leakage current will not be there. So I am considering that overall 50% of the time they are either on or off. Okay, so VDD is 1 volt, and I subthreshold is 1.1675 ampere plus I gate is 0.55 ampere divided by 2, so it will come as how much? It will come as 0.85875 watt, 0.86 watt. See, so this is the answer. This is how we find the total power dissipation in such given conditions. Take a moment, look into it. Fine. Okay, so let's move to the next question, question number 6. So some statements have been given and it has been asked to identify whether they are correct or wrong, true or false. Okay, the first statement is an NMOS pass transistor acting as a CMOS latch is only sensitive to input noise. So let us draw the circuit for this as NMOS pass transistor acting as a CMOS latch. Basically, this is my gate, this is my source, and this is my drain. Okay, so if say the phi is 0, that is it is in opaque state, it is storing the data, and we know the voltage here would be VDD minus VT because it's in pass transistor mode. And if there is a noise of minus VT in the input, okay, minus VT or higher, my VGS value would become greater than VT and this would start leaking, right? So my input noise will affect. So the first statement that it is sensitive to input noise is correct, but whether it is only sensitive to input noise, let us check it. So it is sensitive to input noise. Now for output noise, say there is an draw it again. Okay, so say this is my gate, this is my source, this is my drain, and here it is 0, so it is storing as 0. Here it is also 0. Okay, but now, and say this phi is VDD, that is it is storing 0. My input is 0, my input is 0, my output is also 0, but somehow as this output is also connected to some circuitry, some sense, like some read circuitry or something like that. So say from there a noise came, which is of this form, which is greater than or equals to VT. Okay, my VGS is already greater than VT. VGS minus VT is already greater than 0, and my VT or VDS also becomes here positive, right? So there will be charge sharing between these two capacitors, and I will be getting a voltage here at the Vs. Even if it is not greater than or equals to VT, if it is some voltage also less than VT also, still there could be charge sharing. There will be charge sharing, and my some voltage will be developed in the input. So input driver circuitry that was forcing 0, but still instead of 0 there will be some voltage in the input due to the noise in the output. So it is also prone to output noise. So first statement that CMOS latch is only sensitive to input noise is wrong, because it is sensitive to both input and output noise. Clear? There will be some charge sharing and voltage will be developed here also. Same voltage will be developed in the input and output. Okay. So second statement is a transmission gate acting as a CMOS latch attains full swing. Let us see. This is a transmission gate basically. So this will be D, this will be Q. Phi bar phi, or phi bar, you say. So you can see when my D is high, my PMOS is strong 1, so my Q will be charged to VDD, and when my D is low, my NMOS is strong 0. Okay, so Q will be charged to 0. So I get a full swing from VDD to 0. So the statement that transmission gate acting as CMOS latch attains full swing is true. Though there will be other problems, that this input and output noise would be present. Okay, and this leakage terms will affect, these things will be present, but my swing problem that was present with NMOS pass transistor gate, as NMOS pass transistor acting as CMOS latch will be solved using transmission gate. Okay, now the third statement is what? An inverted buffer acting as a CMOS latch is only sensitive to input noise. So let me draw an inverted buffer acting as CMOS latch. Basically it will be Q bar, it will be D. Fine. Okay, so now let us see whether it is sensitive to input noise or not. So basically if I draw this inverter, if I zoom this, if I draw the transistor level of this inverter, it's basically this. Okay, so it is my D here, and if I call it node X, this is my node X here. Okay, now if in X, if I get a noise of around minus Vt, that was the problem in this case. If I get such kind of noise, you will see that my VGS here becomes minus Vt minus 0, which is around minus Vt. So my NMOS will be still in off condition. Okay, my NMOS is still in off condition. Okay, so it will become insensitive to any kind of input noise. Output noise will be present, like if any noise comes at this node, then output noise will affect it. If it comes here, output noise will affect it, but input noise will become insensitive to input noise. So the third statement, that it is sensitive to input noise, is false. Okay, and the fourth statement is a buffer inverter acting as a CMOS latch is only sensitive to input noise. Let us look into it. Buffer inverter is something like this: a transmission gate, 5 bar, followed by an inverter, node X, Q bar, and D. Now, like, see, whenever we bring a CMOS circuit like an inverter or buffer, you will remember that the noise problem generally vanishes off, because inverters have rail to rail swing. Okay, so from seeing also, you can say that it is insensitive to output noise and only sensitive to input noise. But let us look into it. If this is the buffer, this is the inverter that we are talking about. Okay, and this is the node X, so it's the output. If there are some noises also here, say this kind of noises are present, still this is affecting the drain of the MOSFET, so it will not affect the gate. Gate is connected here, so it will not affect the gate. Okay, so noise at output does not affect the input node in CMOS circuits. Okay, so it will become insensitive towards output noise and only sensitive towards input noise. So what was the statement? A buffer inverter acting as CMOS latch is only sensitive to input noise, which is true. So the correct sequence is false, true, false, true. So this one. Clear? Any confusion? Everything is fine? Can move forward. Okay, let's move forward. Again, we have been given four statements and have been asked to find the correct option. Okay, the first statement is the switching resistance is low in inverted buffer and hence delay is low. Okay, so let us look into inverted buffer and tri-state inverters. First of all, let me draw a tri-state inverter. Okay, fine. So it will be my D, it is my output, and these two are phi and phi bar. This is a tri-state inverter. Now, how to convert this tri-state inverter into an inverted buffer is simply connect these two nodes. Okay, so if I connect them, it will become something like this. D will be there, this D, and phi and phi bar. I have drawn only one D because at a time only PMOS or NMOS will be on. Okay, and this will be my output. Yes. Now, if I consider the sizes, what will be the sizes? You can see the sizes here should be 4, 4, 2 and 2, but the sizes here can be 2, sorry, it would be an NMOS, 2, 2 and 4. Okay, so the resistance here would be, this is R by 2 parallel R by 2, which will become R by 4, crossed by some half of that becomes, and it will become R by 2. Therefore R effective in this case is this R R5 plus RD. R5 is this 2, this parallel this, so it becomes R by 4 plus R by 2 means 3R by 4. So if resistance is 3/4, my current would be 4 by 3 of benchmark inverter. Okay, because resistance is 3/4, current would become 4 by 3 of the benchmark inverter. Fine. So if current is resistance is decreasing, my delay would decrease. Correct. This is for inverted buffer. Therefore, let me write R effective is reducing, implies delay would be low. Delay would also reduce. So the first statement that switching resistance is low in inverted buffer and hence delay is low is true. Correct. On the next statement, what is the next statement? Logical effort of the tri-state inverter is lesser than that of inverter buffer. Okay. Here I found that the current of inverter buffer is 4 by 3 times of I. So I have to find the I have to first draw the benchmark inverter here, because here the current is not same. So here, as current is 4 by 3 of my benchmark inverter would look something like this. Current is 4 by 3, right? Sizing would be 4 by 3 and 8 by 3. Therefore, logical effort of benchmark inverter, not benchmark inverter, what I am saying, inverted buffer, of inverter buffer would be how much? let's see here. Okay, so D will be connected to this 2 and this 4, right? So 2 plus 4 divided by here 8 by 3 plus 4 by 3. So 12 by 3 is 4. So 6 by 4, 3 by 2. But for tri-state inverter, as this red one will not be connected when it is in tri-state inverter mode. Okay, so here you can see the current would be 2244, so it would be same only, I only, not I dash should be here, I only. So for logical effort for tri-state inverter will be 4 plus 2 by, this is the benchmark for inverter buffer. For tri-state it would be how much? 1 and 2. So 1 plus 2, 3. So 6 by 2, 6 by 3, sorry, 6 by 3 is equals to 2. Correct? Therefore, my logical effort of tri-state inverter is greater than logical effort of inverter buffer. So the statement that has been given that the logical effort of tri-state inverter is lesser than that of the inverter buffer is false. Clear? This is why it's false. Okay, the next statement is CMOS latch with output feedback and input inverter has output static but is insensitive to output noise. Okay, let us draw a CMOS latch with output feedback and input inverter. Fine, you guys can always zoom it and you can see it in the PDF version. So number 3. Okay, so let me draw CMOS latch with output feedback and input inverter. There is an inverter in the input. Phi and phi bar. Is basically the this phi and phi bar would be inverse of what is present here. This should be reverse of each other. So that when it is off, it will be on. When it is off, it will be on. Okay. Here it will be Q because 2 inverters are present in the active path, so it will be Q. Okay. See now whether output is static or not. First question. Yes, output is static. Why? If there is any leakage, from X, if there is any leakage through here, if there is any leakage from here, this tri-state mux, what it will do? It will keep on charging it. If it was VDD, it will keep on charging it to VDD. The output, if it was 0 and it was 1, it would keep on charging it to VDD, and if it was 1 and it was 0, it would keep on discharging it to 0. Okay, so my output is static is true, but is insensitive to output noise. See, if there is any noise here, if there is any form of noise here, say any form of noise here, this tri-state mux would amplify it, or even not, it will, if it will not amplify, it will reintroduce this noise to this output, to this node X. Okay, so it is no longer insensitive to output noise, and it is prone to output noise. So the second statement, that it is insensitive to output noise, is false. Therefore, it will be false. Clear? How the voltages will be static, but noise, it will be prone to output noise. Okay, fine. So let's move to the next statement. That CMOS latch with output feedback has the output static but is sensitive to input noise. Let us look into it. CMOS latch, nothing is there in the input, only output. 5 bar. D Q bar 5 bar. Okay, fine. So output is static. Yes, output is static. Why? Because of the same reason that I have given here. Because it will keep on maintaining this, and hence this will maintain this node X, this output node Q bar, and this X should keep on maintaining this Q bar. So the output will be static, and if any noise is present in the input, you can see this noise will be passed and it will affect this node X, and hence the Q bar. Okay, so the statement that CMOS latch with output feedback has the output static but is sensitive to noise, input noise, is true. So the correct sequence is true, false, false, true. This one. Clear? Any confusion? Go through it once again, and see whether you have any confusion or not. Fine. Okay, let's move to the next question. Question number 8. So again, select the correct options. The first statement is a jump latch saves 2 transistors in the feedback path. So let us look into what a jump latch is. So initially in the tri-state inverter based design, we have seen that the circuit is something like this. Five bar, something like this. Okay, correct. Here it will be Q, here it will be T. Okay, now this is the tri-state inverter. So what is the circuit of this tri-state inverter? Something like this. PMOS, PMOS, NMOS, NMOS to be connected. D, and here it is phi and phi bar, because it's reverse of this one. This one is reverse of this one. So here above will be phi bar, phi, below will be phi bar. Header device it will be phi, footer device it will be phi bar. Okay, Now in the gem latch, what is the structure? Same, let me copy it. This is the gem latch. The only difference is, instead of a tri-state mux, it will be an weak inverter here. A weak inverter here. So if it is inverter, what will be the circuit? This will be the circuit. But simple, only the sizes should be small because I want a weak inverter here. So the first statement, that a jam latch ships 2 transistors in the feedback path, you can see instead of 4, a jam latch has only 2 transistors, so it is saving 2 transistors. The first statement is true. Now the second statement is, a jam latch increases the clock load. What is clock load? See, here the clock signals are phi and phi bar, okay, and this phi and phi bar are basically in this circuit. This phi is feeding two circuits, two transistors. It is feeding this one, and this is feeding this one. Similarly, phi bar is feeding two transistors, this one and this one. Whereas in the jam latch, the phi is only feeding one transistor, this, and phi bar is feeding only one transistor, this. So it is reducing the clock load. So in like in any signal, when we are giving this signal, we need driver circuitries, and depending upon the load capacitance and resistances the load it needs to drive, we need to strengthen this driver circuitries appropriately. Okay, so as you have also seen in the delay cases and all. So as to reduce the clock load, what we do, we use weak inverters instead of this tri-state mux. So my jam latch basically incorporates weak inverter, saving not only number of transistors and hence the area footprint, but also reduces the clock overload, not overload, clock load. So the second statement, that jam latches increase the clock load, is false, right? Reduces it. Okay, clear? The third statement is, a negative edge flip-flop. This one. A negative edge flip-flop has the first stage clocked with inverted clock signal, and the second stage is clocked with non-inverted clock signal. So let us look into it. Let us look into the circuit. Basically, it is two latches, one positive edge, one negative edge connected back to back. Phi bar. So it is very Q, it will be Q bar, I guess, because 3 inverters are connected. And you can see here it will be transparent during phi, and this one will be transparent during phi bar. So this is my clock, this is phi bar. So it will sample at this falling edge, negative edge trigger. So a negative edge flip-flop has first stage clocked with inverted. No, first stage is not clocked with inverted. First stage is clocked with a normal clock signal, and the second stage is clocked with inverted. So third statement is false. Clear? Sorry. Okay. Now the fourth statement is, CMOS latch with output feedback and the input and the output inverter is the most recommended latch. Which one is it? Their input and output inverters are present. is my transmission based latch. So let me first draw it and let me discuss whether it has any problems or not. It's Q, it's D. So first of all, transmission gate is used, so rail to rail swing will be ensured. First problem solved. Inverter is present at the input, and so no input noise. Second problem solved. Inverter is present at the output, so no output noise. Third problem is solved. Then this node, it will be maintained. So this node X, and hence my Q voltage should be maintained. So sub-threshold leakage would not affect it because of this weak inverter present here. So this problem of depleting voltages with time due to sub-threshold leakage is also solved. So all the problems are solved. Almost all the problems are solved here. Okay. So yes, it is the most used and most recommended latch design. Okay. So it's true. So the correct sequence is true, false, false, true. Fine. Okay, clear? Sorry. Let's go to the next question. Question number 9. So question number 9 and 10 are basically the similar questions as we have done in the first 4 questions. So let us look into it. How much I have described, is it understandable? Do you guys have any confusion? Okay, if no confusion, we can move forward. So the next question is, for 65 nanometer technology node, find the subthreshold leakage current for a 2 NOR logic with input 1 0, given that subthreshold slope, Debye coefficient, body effect coefficient, subthreshold leakage current for single NMOS transistor, and subthreshold leakage current for single PMOS transistors are given. Okay, so this is S, this is eta, this is K gamma. Okay, so let me draw the circuit first. It is a NOR gate, right? So PMOS stack, input is 1 0, and this is my output stack. One zero. So my output will be 0 because it will discharge it, and charging part is not present. So output will be 0, and this one is in discharge through this path. Okay, so it is off, this is on, this is off, this is on. So as 0 volt is present here, and we know PMOS is strong 1 and weak 0, so it won't be able to pass voltage 0 completely here. It will pass small voltage of VT. Okay, mod of VT. If VT is considered as negative PMOS, then it will be mod of VT. Depends upon the nomenclature you are using. So small voltage VT will be passed, will develop at this node. Okay, now as the output is 0, so, and this is discharging it, so there is no question of anything getting discharged through the subthreshold because it is already discharging it. Okay, so, and also VDS is also 0, so from here also you can see the VD is 0, VS is 0, so my NMOS subthreshold current would be 0, VDS is 0 basically, and even this one is on, so any current it will only discharge it. No question of this subthreshold region of this off transistor coming into picture. Okay, now for the PMOS, I will have a subthreshold current which will be equals to I off, 10 to the power VSG minus eta VSD minus VDD minus K gamma. It was VSB or VBS? What it was? It was VBS. Right, yes, for PMOS, right? So I of 10 to the power Vs in. Okay, so this is my transistor, target transistor. So Vs is VDD, that is 1 volt, Vg is 1 volt, eta is 0.1, Vs is 1 volt, Vd is Vt, that is 0.3, minus Vdd is 1 volt, minus K gamma is 0.066, Vb is 1 volt, Vs is 1 volt by 0.1 volt. So I of 10 to the power minus 0.1, this will cancel, into 0.3 divided by subthreshold 0.1. So 10 to the power minus 0.3 is how much? 0.501. And I of is how much? I of is given as, for PMOS it is 9.3 nanoampere. So it is coming as 4.66 nanoampere. Therefore I subthreshold would be equals to I subthreshold of PMOS should be equals to 4.66 nanoamperes. Fine. 4.67 nanoamperes. Clear? Okay. Okay, then let's move to the next question. Question number 10. For a 65 nanometer technology node, find the subthreshold leakage current for a 2-node logic with input 0 0, given that all the parameters are given. Similar, I'll be drawing the 2 input now again. So input is 0 0, so it would be, output would be VDD, that is 1 volt. Okay, and both the NMOSes are off, so both the NMOSes should contribute to subthreshold leakage. And as no stacking is present, simply my subthreshold leakage current for a single NMOS is given as this one. So it will be, for 2 transistors, it will be twice of this one. Okay. So, but for simplicity, let me show the calculation as well. I subthreshold should be I of 10 to the power VGS. VG is 0, Vs is 0, plus eta is 0.1. Now VDS is how much? 1 minus 0 minus VDD is 1 minus K gamma is 0.066 V BS, right? VSB. So Vs is, source is 0, B is 0, 0.1. So it's basically I of 10 to the power 0, that is 1. So I of, for 1, I have for 1 NMOS. Okay, which is equals to 5.63 nanoampere. Now total I subthreshold total will be twice of I subthreshold for NMOSes, because there are 2 transistors in off region. So twice of 5.63 nanoampere is how much? 10, 11.2, 11.26 nanoampere. Here the answer is 11.62. It is I think typing mistake, typographical error. It would be 11.26 nanoampere. Clear? Any confusion? check the 10 questions. Any confusion in any question? First question, second question, third question, fourth question, fifth. So first 1 2 3 4 5, almost even 5, and then 9 10 are same kind of questions, questions with same kind of flavor. And question number 6 7 8 9 does not deal with this power as such, but it deals with designing of this sequential circuits, how we came to the design of flip-flop, how a flip-flop has been designed starting from the initial approaches, initial tries, initial approaches, then how it was evolved over time to the most used flip-flop circuits. If anyone has any question, you can kindly ask. No questions today? Okay, so if there are no questions, then we can call it a day. See you next week with week 11's discussion session. In the week 11's discussion session. So thank you for attending. Have a nice day.